Okay, we're going to do this question on normal distribution. I've chosen this question specifically because it covers pretty much everything there is on normal distribution. Okay, so we have what to do when mu or sigma is unknown, we have doing calculations, we have doing a normal approximation, and we also have hypothesis testing. So let's start straight away. First thing is part A, where when you read it, it's maybe not immediate, it's a unknown mu or unknown sigma. But whenever there's any question where it doesn't tell you both of the mean and standard deviation, you should do this technique. You should always go and find them. So what do we know? We know the mean mu is 25, and we don't know sigma. Again, whatever it's asking us, we're going to first have to find that unknown sigma. So how do we do that? Well, I like to do a little diagram to remind myself of the calculations. So I would say, what do I know about my distribution? I know that the average here is 25. And I also know that 15% contain less than this. So the probability that what's the amount? The amount is D is less than 24.63 is 15%. So I'm just going to add that on over here. So there's 24.63. Oops. And there's my 15%. So the way that we find mu or sigma or both when they are unknown, we have to convert to a z-score. Okay, so this is like my distribution D. And I'm going to take that and convert to z. So remember the formula. Z is how many standard deviations away from the mean we are. So it's going to be D minus mu over sigma. And z-scores are always normally distributed with mean 0 and standard deviation 1. So on the z-score, I have the mean is 0. And I still have a 15% region over here. And the kind of question is, well, how much is this region? And that will sort of correspond to 24.63, right? It'll be the z-score of 24.63. So the calculations you actually have to write down, okay, the probability that D less than 24.63 is 15%. That means the probability that the z-score is less than or z, remember, is x minus mu over sigma. That's going to be the same probability. I've got that from my picture, right? It's the same probability being less than this value. Now, you can use the inverse normal function on your calculator, okay? If you know there's a 15% chance of the z-score being less than a particular value, and you know the full distribution for z, don't you? You can find question mark, you do the inverse normal. So the area is going to be the area to the left, which is 15%, and then mu is always going to be 0, sigma always going to be 1 because it is z. So over here, my working, I'm going to write 24.63 minus, now mu was actually 25, so I'll put that in there, over sigma. So again, I'm going for the inverse normal function on my calculator. I put an area to be 15%, and I get negative 1.036, so on. I'll do a few more decimal places. Okay, so that's this number here, negative 1.036. And yeah, so I get my equation, I change it to a z-score, keeping the area the same. I do my inverse normal function to change that area to a z-score, and then I have my equation here relating sigma to a bunch of other numbers, and you can just solve for sigma here. And if both sigma and mu are unknown, then you'll get two unknowns in your equation, and you'll have two equations, so you solve them simultaneously. I'm sure you've seen this before. So 24.63 minus 25, all divided by that, 0.35, 0.35699. So I guess we could say 0.537 to 366. That wasn't the question though. The question was actually now, I know the full distribution, so now I can answer any question relating to the distribution. Okay, so continued over here. Find in two decimal places the value of k, such that this is true. Well, this is more like a standard question. So again, a picture is really going to help you know how to sort out your calculations here. We're looking for the value where between 24.63 and k is 45%. Okay, 24.63. K is from over here, and I have 45% in the middle. So again, because my unknown is a value over here, it's like a value on the axis. It's an amount. It's in milliliters. I'm going to have to use the inverse function to find me that based on the area. And the inverse function in your calculator will take the area to the left. So I need the area to the left of k. Well, I know 45% in between 24.63 and k. That's from the question. I also know to the left of 24.63, I could just calculate it, because I now know the distribution, right? If mu is 25, I think with this. But we actually also know this is just going to be, what was it, 15% from earlier. That's how it's the same number. This 24.63 is the same number here, so it's just at 15%. So I'm going to again do the inverse normal. The area to the left is 15% plus 45% is 60%. Here, mu and sigma, this is the original distribution D. So they're going to be, as we had in the question, as we just calculated. That tells me that k will equal, so I'm just going to go and edit what I had in my calculator. So I need to put the area 0.6, 0.35. I'm going to type in 699 in my calculator, just as many decimal places as possible until the final answer. And I get 25.09. 5.090. That's milliliters. It doesn't say to, oh, it says 2 decimal places, so k equals 25.09. We're done there. Okay? So, unknown mu, unknown sigma, you just start your equation, convert to a z-score, and then inverse function. Remember to always get the area to the left, so you have to convert. Okay. Part B then. Part B says a random sample of 200 bottles is taken using a normal approximation, find the probability, blah, blah, blah. So, common question is, how do I know when to use a normal approximation? And the answer is very easy. Only if they tell you. Okay, so if they tell you normal approximation, that's when you do it. Otherwise, you're not going to do it. So we use a normal approximation. Find the probability that fewer than half the bottles chosen contain between 24.63 and k. So the normal approximation is when you have a binomial distribution and you're trying to find a normal distribution that is roughly the same. So we need to start by saying, well, what is the binomial distribution we're doing? Well, we are having 200 bottles and we want to know how many contain this amount of liquid. So my binomial is going to be is counting that number. Binomial is counting. N is 200 bottles. And the probability of any given bottle being between 24.63 and k milliliters, well, actually, that's already stated in the question. That was 45%, right? So I'm taking 200 bottles, and each one of those 200 has a 45% chance of having this much liquid. So the number of bottles I get, which is x, so x is the number of bottles between 24.63 and k, and that would be multiplied by the binomial distribution, and p was 45%. So first step, I found my binomial. Second step, let's approximate that with the normal. So what normal approximates this? Well, you just need to know the general formula, that it's going to be the mean NP, and variance is NP bracket 1 minus P. This is kind of in the formula booklet. If you look at the table with standard deviation, if you look at the table, it's underneath the standard deviation stuff. It's got the distribution, the binomial distribution, and it will say mean, NP, and it will say variance, NP 1 minus P. So it is kind of in there, in that form. So Y is a normal distribution. Now NP here, let's just calculate. NP is 200. Remember, this is N, this is P. N is 200 times 0.45, so that's going to be 90. Put 90 over here. and then quick calculator check. So 90 times 1 minus p is 49.5. And remember, this is my variance, so my sigma is actually going to be the square root of 49.5, whatever that is. Okay, so step 1, done. Step 2, done. Step 3 is the continuity correction. Okay, there's many ways you can have this explained to you. My simplest way is this. We want the probability of how many bottles? Well, we want fewer than half. So 200 bottles are taken. So fewer than half will be less than 100. If you want to approximate, the difference is a binomial distribution can only be whole numbers. So these are the whole numbers, 99, 98, 97, and so on. I like to write it with a less than or equal than, or a greater than or equal than, if it's given with this. A normal distribution can have all decimals. So what you need to just include here is any decimal number that when you round it to the nearest whole number will be one of the numbers you're interested in. So the numbers we're interested in are 99, 98, 97, so on. So the decimal numbers that includes are anything below 99.5, right? Anything 99.5 or lower is going to round down to 99 or lower. Well, you might say 99.5 actually rounds up. Yeah, true. But remember, a normal distribution is a continuous. So the probability of y being any specific number is actually 0. And we can just always use this strict inequality here. You can write less than or equal than, it'll be the same value. So I'll just write it strict. I've got all numbers that round down. Another way to kind of think about it is you're making your error slightly bigger, right? Instead of being 99 or less, it's now 99.5 or less. So the area always gets a little bit bigger. Try and remember it like this, and don't just say, oh, it's going to be just one less than the number, because what if I gave you x greater than 20, or probability x is greater than or equal to 13, right? All of these numbers, you just think which decimal numbers round to it. So if this was the question, which decimal numbers round to something more than 20, well, that's going to be anything which is 20.5 or more, because this is greater than or equal to 21. Yeah, greater than or equal to 13, again, which decimal numbers round to something which is 13 or more? Well, that's 12.5 or more. That's the rule. It's simple as that. Okay, so this is our approximation. We're approximating x less than 100 with y less than or equal to 9.5, and we know y. We've written the distribution of y right here. So I'm going to put that in my just regular normal CD. Upper bound is 99.5, and the lower is -1 with a few zeros on the end. Let's see what that tells us. 99.5 there. Sigma was the square root of 49.5, remember here. And mu was 90. So we reckon, what's that? Equals, does it say number 6 fig? It doesn't. So 91 or 0.9115. We'll leave it there. So 91% chance, which seems reasonable to me because it was a 45% chance. So you would expect less than half when you take such a large sample size of 200. Right, so normal approximation covered there. We have step 1, you find your binomial. Step 2, you change, you find NP and NP1 minus P to change it to a normal. And then step 3, tricky part, you do the continuity correction. So you pick all decimal numbers that would round to make the whole numbers you're interested in from your binomial. And then you just get your calculation from there. Part C. How are we going to do part C? Part C was hypothesis testing. So just be aware that they sometimes are totally unrelated. So actually, it's now adjusted. So we know the standard deviation is now exactly 16 or 0.16. The mean is still the same by the looks of it because Hannah believes the mean is now less than 25. But we're testing against that. That'll be H0. So we're keeping that unchanged. Okay, so hypothesis testing, you know the drill. Start off with H0, H1. You have to read the question here. H0, well, yeah, we're going to assume the mean is still 25. And what does she believe? Does she specify? She specifies she thinks it is less than. So I can say alternative hypothesis mu less than 25 milliliters. And we're going to have, let's say X be the amount in a, what was it, bottles or, yeah, bottle of perfume. So hypothesis testing with a normal, remember, you have to do the sample mean, because what we're doing, we're assuming H0, and what we're interested in actually is the sample average, because what she does for her experiment is she is taking an average, well, she's taking 20 bottles and find the average of that sample of that 20. So remember the formula over here. If X was normal with mu and sigma squared, then the sample average is normal with mean mu and variance sigma squared over n. So in particular, the standard deviation is has been divided by the square root of n. So here, x bar is normally distributed. Mu is still 25, but instead of, what was it, 0.16, okay, instead of 0.16, because I'm taking a sample of 20 bottles, 0.16 has to be divided by the square root of 20. And that will become my new standard deviation. And it was 0.16 before, not the variance. Yeah, that was standard deviation. Brilliant. So, first thing to tip you up on the hypothesis testing is the sample average, where you adjust the standard deviation. I've adjusted the standard deviation, so now I can get on with it just as you would do with binomial or any hypothesis testing. So, we calculate what we observed. She observed 24.94 milliliters. Okay, so what is the probability that we got 24.94? Now you always go less than or greater than. I mean, we can see we'll have to do less than based on this, but you can also just do a very quick check that if the mean is 25 and we are down here at 24.94, you always do this sort of small tail, which is away from 25 to the left. So we calculate probability x bar less than 24.94. Again, for the calculator, lower will be negative 1,000, upper 24.94. And make sure for sigma we're putting not 0.16, but we're dividing by that square root of 20. And mu could be 25. 0.0468, that is. Okay, there's my p-value. Remember, if it's a two-tailed test and it asks for the p-value, you have to double it. This is a one-tailed test. And we just make our conclusion now. 5% level of significance. So this p-value is less than 5%. So it is very unlikely. It's even more unlikely than 5%. So it's significant. Significant means I reject my past thinking. I reject H0. And in context, there is sufficient evidence that, well, can I just write to support so-and-so's claim? I can, to support Hannah's belief. Or write it out fully that the mean amount is less. Mean amount of liquid in each bottle is less than 25 milliliters. Feel free just to write to support Hannah's belief. Take yourself a bit of writing there. Okay, so yeah, we've kind of hopefully gone through that fairly quick. You can hopefully use these to answer any kind of question on normal. It doesn't have the critical regions and hypothesis testing, so maybe that would be for another video. We'll try to do a few more stats ones, do some probability and some linear interpolation, just quick topics that you can just fire off if you need a reminder on your revision. So good luck with all that, and thank you very much.